Hey everyone! In this video, I'm going to give you a programming/coding interview problem for which you can use dynamic programming. If you're not familiar with dynamic programming, I'd recommend my dynamic programming introduction video first. So here's the problem. You're given an array of integers, for example 2, 4, 6, and 10, and you're supposed to find subsets of this array which add up to a certain number, for example 16. So in this case, there are two such subsets. The first one is 6 and 10, and the second such subset is 2, 4, and 10. And just to make the problem a little bit simpler, you don't have to actually find the subsets themselves. You just need to find the number of subsets that add up to the given number. So in this example, your function should take this number 16 as well as this array and return 2 because there are two subsets of this array that add up to 16. Now, when you're given a coding interview problem like this one, the typical first step is to ask some clarifying questions. So you might ask as a clarifying question, is it possible to have negative numbers here? The answer is no. We only have positive integers here, so there's no zeros or negative numbers. And is this array already sorted? Actually, it doesn't matter too much if it's sorted or not, but let's just say it's sorted. And are there any duplicates in this array? So is it possible to have two of the same number? The answer is no, there are no duplicates. And what if you're given, instead of 16, 0 as one of the arguments? What should we return then? In that case, you should return 1 from your function, because technically the empty array or the empty set adds up to 0. So you count just this set and you return 1 from your function. So think about this problem for a second and then come back for a solution. So if I was given this problem, I would first ask myself, how would I solve this problem on a whiteboard or on paper? The way I would do that is I would start with an empty set and I would try and construct all the possible subsets of this array. So for the rightmost element, or you can start at the leftmost element, but let me start with the rightmost element. For that one, we need to ask ourselves, do we want to include it in the subset that we're trying to construct? If the answer is yes, we'll have a subset of just one element, 10. And if the answer is no, we'll still have an empty set. And we'll need to do the same thing for the next element, 6, and for each of these subsets. So if we decide to include 6 to this subset or add 6 to this subset, we'll have 6 and 10. And if we decide not to include that in this one, we'll have just 10 and so on. So just like that, you'll be able to find all the possible subsets of this entire array. And for each of these subsets, you can just ask yourself, in theory, does it add up to, for example, 16? And then add up all of those subsets, and we have the answer. And when I see this structure, if I was in the actual interview, I might say, well, since it's a tree, it actually looks like a recursion tree. And so maybe I can solve this problem using recursion. So let's see how we can do that. Of course, the idea of recursion is to break down the large problem, the original problem, into smaller subproblems that are similar in nature. So let's see how we can do that. Let's call the number of subsets that add up to 16 out of the entire array n. That's the answer that we're looking for. And this n is actually the sum of two numbers. And the first such number is the number of subsets that add up to 16, which include 10. And the second such number is the number of subsets that add up to 16, which do not include 10. And actually, this first number, the number of subsets that add up to 16, which include 10, is equivalent to the number of subsets that add up to 6 out of these 3 elements. So the subsets that add up to 6 out of these 3 elements are 2, 4, and just 6. And you can sort of merge each of these subsets with this subset with only 10 and get a subset that adds up to 16. We can get 2 of them. So we can put 2 here as the first number, and the second number, that the number of subsets that add up to 16 which do not include 10, is equivalent to the number of subsets that add up to 16 out of these 3 elements, because we don't have this in play anymore. And there's no such subset that adds up to 16 out of these 3 elements, because if you add all of them up, you'd only have 12 as the total sum. So you'd have 0 right here as the second number. So in this particular example, the answer that we're looking for is n is equal to 2 plus 0, which is 2. So what we just did is we broke down the large original problem of finding the number of subsets that add up to 16 out of this whole array into 2 smaller subproblems. And we can actually keep going like that further down the tree as well. Just keep breaking down the problems into smaller and smaller problems. So this is the basic idea of my recursive solution. But one thing to note here is that you don't really have to create or store these individual subsets, because we are only interested in the number of subsets that add up to a certain number, for example 16. We only need to store the sum of each subset. So the sum of this subset would be 10, and then the sum of the empty subset is of course 0, and the sum of this one is 16, and the sum of 10 is 10, and so on. Okay, let's now see what this solution might look like in code. Okay, here's my recursive solution in code. I'm defining 2 functions here, countsets and rec. Countsets will be our main function. It'll take the array, this given array, and the total amount that we're trying to find the subsets for, and this is going to return the number of subsets that add up to the total amount. And then rec will be our recursive function, so it'll call itself recursively, and it'll take the given array, the total amount, and I as an index. And this is going to return the number of subsets that add up to the total amount, but while considering only the elements up to the index I. So if you're given, for example, this array R and 6 as the total amount and 2 as the index, that would be right here, we're only considering these 3 elements to find the subsets that add up to the given amount. And in that case, your function rec should return 2, because there are 2 such subsets, 2, 4, and 6. Both of them add up to 6. And the only thing we need to do in count sets is to return rec with the arguments r total and r.length minus 1, because r.length minus 1 would be the last index of this array. In this particular example, that would be 3. Okay, the first thing we need to do in the rec function, or the recursive function, is we need to take care of some base cases. The first one to take care of is when total is equal to 0. In that case, we should return 1, because when total is 0, the only subset that adds up to 0 is the empty subset, and there is only one of them. And the second base case to take care of is when total is less than 0. And if that's the case, there is no subset that adds up to 0, so we should just return 0 since there are no negative numbers in this array. And if I is less than 0, that would mean I is already outside of this array. And since we know that total is neither 0 nor less than 0, total here is a positive number. And since we don't have any more numbers to create a subset with that add up to hopefully total, we'll just return 0. And if none of these cases are true, we'll then go to our recursive cases. The first recursive case that we need to deal with is when total is less than r square brackets I, or the last item that we're examining. So for example, if I is equal to 2, we'd be examining this item. 6 would be the value of r square brackets I, and if the given total here is, let's say, 4, there would be no way of finding a subset out of these 3 elements that add up to 4, which includes the current item, 6. So that means the number of subsets that add up to the total amount out of these three elements is equivalent to the number of subsets that add up to the total amount out of these two elements instead. To express that, we'll just need to write return rec r total I minus 1. So r and total are unchanged, and we'll just need to go to the next item, or the item that's left to the current item that we're examining. Other case we need to deal with is everything else. So let's say I is equal to 2 here. So we're examining this item currently, and the total that we're looking for is 6. If that's the case, we'll need to deal with two different cases just like I explained before. The first case is when we don't include 6 in the subset that we're trying to construct, and it's the same as before. So we'll just need to write rec r total I minus 1. And the second case is when we do include this item in the subset that we're trying to construct. And just like I explained before, the way you can think about it is this. The number of subsets that add up to the given total, 6 right here, which include this number 6, is equivalent to the number of subsets that add up to total minus the current item. So total minus r square brackets I out of these two elements only. So you can find that with rec r total minus r square brackets I. So that'll be the new total that we'll be looking for subsets for, and I minus 1 to go to the next element. And that's my recursive solution. Okay, and this solution works, but the problem is it's not very efficient. The problem is that we're going to call this function rec with the same arguments, r total and I, over and over again. And this will be particularly the case when the given array is very long, very large, and the given total is very large as well. So of course, dynamic programming says, why not just store some of those return values for the same total and I, so that we don't have to repeat the same computation over and over again. So let's see what a dynamic programming solution or a memoized solution looks like in code. Okay, here's my dynamic programming or memoized solution. Just like before, we're gonna write two functions, dp and countsetsDP. CountsetsDP will be our main function, which will return the number of subsets that add up to total given the array. And dp will be the function that'll call itself recursively. But note here that we have an additional argument here called mem, which we're going to use to store the return values for some arguments for this function. The first thing we'll need to do in countsetsDP is we need to initialize an empty dictionary or hash table, depending on the language, and then assign it to mem, because this is what we're going to use for storing the return values. And then call dp with the arguments r total, r.length minus 1, and then mem. Okay, in dp, the return values for certain arguments will be stored in mem in key value pairs. Each key will represent a unique set of arguments, and there will be an associated value with it, and that's going to be the return value that's stored for this function dp. So we need a way to create a key, which is going to be a string in this particular case, from the pair of arguments that change total and I. There are several different ways of doing this, but what we're going to use here is a very simple method. We're going to convert total and I, which are integers, to strings, and then we're going to concatenate them with a colon between them. So for example, if we had 10 as total and 3 as I, we'll have this string 10 colon 3 as the key. And we don't necessarily have to use this particular string, but we just need a way to uniquely identify each argument pair with a string. And then if this key already exists in mem, that would mean that we've already calculated the return value for this particular total and I pair. So we're just going to return the stored value, the value that's associated with this particular key, instead of going through this whole function. And if we don't have any stored value associated with this key yet, we're going to go through this whole function, and it's going to be very similar to what we had earlier for the recursive solution. First of all, the base cases are exactly the same. So we're just going to skip that. And else, if total is less than r square brackets I, we have dp of r total I minus 1 mem, which is almost exactly the same as what we had earlier in our recursive solution. But instead of returning this right away, we're going to store it in the toReturn variable, and then we're going to return it at the end. And we're going to take care of the other case the same way. We have dp of r total minus r square brackets I minus 1 mem, and then the same thing as what we had right here. So add them up, and instead of returning it, we're going to store it in toReturn. And after that, before returning toReturn, we're going to store it in the mem dictionary or hash table with the key, which we calculated earlier, so that we can use this value later when we see the same pair of arguments. And of course, at the end of this function, we're going to return toReturn, and we're done. This is my dynamic programming solution, but let's see if we can calculate the time complexity for this function. To find the time complexity for this method, we first need to find the number of times we call our recursive function, dp, and then multiply by the time it takes to execute each of those calls. So let's first see if we can count the number of calls we call dp. There are only two ways we call dp. The first one is from right here, from the original function counts sets dp, and then the second way is from this block right here, either on this line or this line. And now the important thing to notice here is that the number of times we call this block is at most total times n times, where n is the number of items in the given array. And you can think about it this way. There are n potential values for I ranging from 0 through n minus 1. And the number of potential values for this argument total is the original value of total. So if the original value of total is 16, and if you're given this array, n would be 4. So you'd have 16 times 4 potential value pairs for the pair total and I. And for each unique pair, we only go through this entire function and then get to this block once, because after the first time, we'll already have returned here. And if either total or I is out of range from those particular pairs, for example, if I is minus 1, then we'll already have returned before we get to this block, for example, right here as well. And so we get to this block at most total times n times, and each time we get to this block, we'll call dp only at most twice. So the maximum number of times we're going to call dp is going to be total times n times 2, and if you want, you can add 1 to account for the first time we call dp from count sets dp. So now we have an upper bound for the number of times we're going to call this function dp, and that's total times n times 2 plus 2. And of course, total here is the original value of total. And what about the time it takes to execute each of those calls? If you look at each line in this function, except for those recursive calls, each line only takes a constant amount of time, or big O of 1, to execute. And of course, when you add up a bunch of different operations, each taking constant amount of time, they will only take a constant amount of time as a whole. So the time it takes to execute each of those calls, excluding those recursive calls, is big O of 1, or a constant amount of time. And when you multiply these two numbers together, big O of 1 and total times n times 2 plus 2, you get big O of total times n being the number of items in the given array. And so that's the time complexity for this particular function. Okay, just like usual, let me know in the comment below if anything is unclear. And if you like this video, I would also recommend my course on Udemy called 11 Essential Coding Interview Questions, in which I cover 11 of the most essential coding interview questions to master. Although I don't cover dynamic programming in this course, but I'm going to put a link to this course in the description below. And if you want to make sure that you don't miss my future videos, the best way to do that is to subscribe to my newsletter by going to csdojo.io/news. I'm YK from CS Dojo, and I'll see you in the next video.